All right, so good afternoon, everyone, and thank you for joining. So today we have the pleasure of having Dr. Michael Posa from UPenn as our speaker. So Michael is an assistant professor in the Mechanical and Applied Mechanics department at UPenn, where he leads the Dynamic Autonomy and Intelligent Robotics group, which falls under the GRASP lab at UPenn. And his group mainly focuses on developing computationally tractable algorithms to enable robots to work in unstructured environments. And Michael received his PhD at MIT, working with Dr. Russ Tedrick in 2017, where he also spent some time on MIT DARPA Robotics Challenge. He got his BS degree from Stanford in 2007. And while before starting his PhD, he also worked at Vecna Robotics, which is also in Cambridge, where he worked for developing control algorithms for Bayer humanoid robot. So he has been working for a long time on different contact-rich problems in locomotion as well as manipulation. He has also received a lot of awards. So he received the Google Faculty Award in 2019 and a Young Faculty Award from TRI in 2021. So we are really excited to have him here. And with that, the stage is yours, Michael. Please feel free to share a slide. And for everyone else, like I'll be moderating the session. So please put yourself on mute and raise your hands on Zoom whenever you feel like asking a question. And we'll ask the question to Michael at the appropriate time. Thank you very much.
Thank you for the introduction, Devesh, and thank you as well for having me out here. It's excited to sort of share what we're working on and also learn a little bit about more about MERL. Great. Okay, so the title of the talk is Hybrid Robotics and Implicit Learning. This implicit learning work, which I'll get into, is something I've really gotten into in the last couple of years. Very excited about, and it builds off some of the things that Devesh was saying related to our work on multi-contact. Okay, so everyone's seen this video before. We don't need to dwell on it. It's amazing. What Boston Dynamics is doing is really, really astounding. And I think, maybe we wouldn't have believed this was possible, 5 years ago. And even this video is already, a couple years old. Okay, as neat as it is, right? As impressive as it is, you compare that now to humans, whether that's people doing parkour or maybe just in-home and cooking. Now, obviously, these are both cases of expert humans, but the humans remain, really worlds apart from the robot, right? As impressive as the Atlas is, the way it's going about its parkour moves, its jumping, has been very, very carefully prescribed by engineers, planned in advance, executed to an amazing degree of skill, but still a far cry from the dexterity that the humans are showing. So how do we kind of bridge that gap? Well, the problem that's really motivating me in the last few years sort of goes like this, right? My robot is going to enter some environment, and that environment is going to be novel to it. There's going to be new objects, potentially new tasks that it's not seen before. So it doesn't have the ability of foresight to go off and train for 1,000 simulated years in simulation and come back with a policy. It doesn't have time to go out and collect massive amounts of data or plan offline with the model. Whatever it's going to do, it's going to have to do with minimal amount of information. So it's going to have to understand its environment and select and execute actions and do so in a matter of seconds or at least a few minutes. I sort of don't want to get into this debate today, but broadly speaking, everything you're going to see here today is going to be model-based. We're going to do some model-based control, and then as well some model learning, which you could then apply to model-based control. Okay. So what could go wrong, right? My robot's going to encounter some environment. The things it's going to encounter are potentially very complex geometrically and non-trivial, right? This pair of tongs, it's not seen before. It has an internal degree of freedom. It's got complicated shape. Maybe it has complicated surface properties, right? Maybe it's hard in some parts and squishy in others. Maybe it has different frictional properties that are going to vary across the surface. And at the end of the day, the things I want to do with these objects are contact-rich, right? They involve touching the objects to one another, to the robot, and to its environment. Okay. So today, we're going to make a little bit of progress right towards this goal, but really barely going to talk about robots for a good chunk of the talk and really just talk about some fundamentals. So physics-inspired fundamentals. Talk a little bit about control at the beginning, some model-based control, particularly with some late results there. And then the last two parts here are going to really focus on learning models from data, or doing system identification if you prefer the original terminology for it. So first, why that's hard in this setting, and then also how we can improve on baselines. Okay. First, just going back in time a little bit. This is work from my PhD at MIT, and sort of had this basic question, right? Of if I want to make a plan for a robot that's going to be encountering touching its environment, whether it's running or manipulating an object, it needs to make some decisions about what to touch, where to touch it, and when to touch it. And this decision making is inherently hybrid, or requires deciding some sort of binary variables. And gradient-based schemes here really struggle, right? So this is sort of the first realization here, that gradient-based optimization can't really reason about mode variations. If I want to get this ball to the star, I can sort of toss it in the air and use some gradient information about how it might get there. But no amount of gradient information is going to tell me that I could also do a bounce pass. Right? I could throw this ball off the ground and bounce it to the star, right? So there's actually two modes here, and gradient exploration is really only going to explore one of them. Okay. What we did back then, and this is 2013, 2014, was develop an optimization strategy, which we called contact-implicit trajectory optimization, which took that hybrid structure, that binary structure, and embedded it with nonlinear constraints. So we didn't change the underlying fundamental problem of this hybrid decision making, but we replaced the hybrid problem with a nonlinear constraint, and the hope that gradient-based optimization could then be successful. All right. So that sort of was older work, and that was all very much offline planning. And back in 2013, 2014, after getting these nice trajectory optimization results, I said, okay, the next thing to do is I want to develop a controller that can be online and can stabilize these systems, feedback basically in these domains. And it turns out, so that was 2014. Again, it took about 8 years, and now finally, okay, we have something where I'm excited to talk about. Before that, though, some preliminaries. The talk today is a little mathematical, and I'll try to sort of key in on where the mathematics is necessary and where it's just sort of interesting for those who work in this space, because I know a lot of people here are working on very similar looking equations. All right, so we are going to represent the hybrid dynamical system part of this when to touch, where to touch, how to touch it, via what's called complementarity systems, which is a form of DAE. So I have some differential equation, x dot equals f of x, x is state, u is action, and then lambda here is going to be some kind of slack variable. Often it's going to be something like a force. Okay, and lambda is going to be subject to some constraints, in particular this complementarity constraint with some function g. A common example here might be a frictionless contact, where lambda now is a normal force, g is a distance, and this complementarity constraint basically says that unless the distance is 0, then the force has to be 0 as well. So you can only exert a force when you're touching. And this is how you get this binary hybrid constraint down to a nonlinear constraint. It's a nasty nonlinear constraint. It's hard to solve, it's hard to optimize over, but it's at least one way of encoding the same phenomenon. And another way to think about this is as an implicit definition of dynamics. Right, so we have x dot, rather than x dot equals f of xu, we have x dot equals f of xu lambda. We've lifted up the problem, right, by introducing this extra slack variable, but then we've constrained that slack variable, right, via this relationship with state and force. And we can also do things like locally linearize, and this is a framework that'll come up a few times. This is a discrete time variation on this. It's called a linear complementarity system. These are basically piecewise-affine dynamics, the subclass of piecewise-affine systems, where the pieces are defined by the different modes. So here's just a toy example here. Consider this falling ball. Okay, it's a point mass. It's going to fall. It's going to stop. It's about as simple as it gets in terms of dynamical systems. So it accelerates downward with gravity. If it ever hits the ground, then the velocity becomes 0. It doesn't even bounce. We're making this very straightforward. We could discretize this system in discrete time. This is what's often done in simulators. And we get a discrete time system that looks something like this, where we have a case structure for our velocity update, which says, oh, okay, if you're not going to hit the ground, then the velocity goes down by gravity. And if you are going to hit the ground, then we have some relationship that velocity is going to satisfy. Okay, and we can write this as an LCS. The math's not super important. I think maybe one interesting thing here to call out is the fact that we have this 1 over delta t. So we took the instantaneous impact event from the original hybrid model, and in discrete time that becomes this 1 over dt stiffness. I'll come back later. The equations here are not super important though. Okay. So again, years ago, wanted to take a trajectory like this, which we developed in simulation, and now actually run it in a real system, which requires feedback. The feedback problem that we posed looks like this MPC problem here. So this is your traditional MPC problem here in black, where we've linearized everything. And the blue is showing the complementarity structure. So in fact, it's not a local linearization, it's a local linear complementarity system. And that's because we need to preserve the ability to reason about nearby modes. If I get bumped off my nominal mode sequence, I need some ability to sort of plan in those nearby modes. Because of that stuff in blue, this is not a QP, it's a quadratically constrained QP. Alternatively, it's a mixed integer QP. Neither of these are particularly tractable, but that's what it is. Okay. And then we want an algorithm here that can run in real time. Okay, so before describing our algorithm, right, I want to sort of lay out the key needs or requirements for such an algorithm, because a lot of people are working in similar domain right now. And I think it's important to elucidate sort of what I think is really important. First off, before even saying this, we cannot solve this MIQP optimally, right, globally, because it's going to take too long. It's going to take seconds, not milliseconds like we needed to do. And so we're going to have to cut corners. We're going to have to make sacrifices. And that's why we want to know what we're giving away, what we want the algorithm to be able to do, given that it's going to make, let's say, suboptimal decisions. So first off, the algorithm should not assume a nominal mode, because that would just be local linearization, and we need to be able to reason about nearby modes. We also can't even just assume the current mode, right? You can't just linearize about your current mode, because we might need to explore, might need to plan back for a different mode sequence. We also need a pretty big prediction horizon here. We can't be myopic. And the reason for this is often my objective function has been designed for my nominal mode. Right? I make a plan to say run across this gap or grasp an object, and my plan is baking in assumptions about what I'm going to touch and when, and my cost function is sort of related to that mode. Right? And so if I want to get good value, let's say out of my final cost here, then I need a prediction horizon that's going to see me back pretty close to my nominal mode or back to my nominal mode. And then lastly, we need this to run fast. It's going to have to run online at real-time rates. So this is all sort of driving it to suboptimal decision making. Okay. So this is work that's actually going to be published at ICRA this year. We just heard we got nominated for the best dynamics and control paper. So excited about that. Sort of key results here are we can solve this at real time. We can solve this, let's say around 30 Hertz, just to give an example here, for a 10-state system with a prediction horizon that also of 10 and 3 contacts with friction. So that's 36 possible modes in this case. This is a 2 fingers in red, kind of manipulating a blue object, a planar object in blue that can also touch the ground. I'm drawing here contact forces that are being determined in real time. Okay. What is this algorithm? It's essentially a consensus ADMM. Okay, so consensus ADMM actually works really well in this domain with a couple of tweaks. The ADMM stages are fairly familiar. The first stage is actually just your normal QP, ignoring the complementarity constraints. And the second stage is a projection back onto the complementarity constraints. That's the hard part. The beauty of the consensus formulation is that those predictions actually become independent in time, at least in prediction horizon. And so we have a number of small independent projections. They can all be performed in parallel, trivially. And we can perform those predictions by solving MIQPs or even approximately solving them with heuristics. Then you have your last dual update. Okay. The last example I showed was simulation. This is a real problem here. So this is a card pole we built in the lab, but it's a card pole that can bounce into these walls, these foam walls. In order to stabilize this, you have to run your controller at tens of hertz at minimum. And you can see here it's making real-time decision making to stabilize this system. This is actually also an example of note where linear control often fails. So if you don't reason about the contacts, you will fail almost certainly. Okay. And this is, to my knowledge, at least, sort of the first example of any kind of real-time MPC, multi-contact MPC in practice on a real system. This is a related but slightly older work here, where I'll mention it briefly in the interest of time. This is purely reactive. Here we're not doing any kind of planning. We've designed a policy, a linear policy here offline, actually uses force measurements. And by using force measurements can provably stabilize these complementary systems. And so this is sort of offline, we're solving bilinear matrix inequality problems, but also generating Lyapunov functions. Okay. Now switching gears here for the rest of the talk, that's I think what we can do with a model, a simple model. I think we're really sort of getting close to real-time control for things like manipulation. Where does that model come from? Well, we have to identify, we have to learn from data somehow. And so this is the problem I want everyone to have in their heads right now. Okay, we're going to be given data that looks something like this. This is a single object moving, and we're looking at its trace of its pose in SE3. So this is our data. And the goal now is going to be able to figure out what is happening here to generate a predictive model from data that looks like this. Okay, so if I were to ask the audience here, maybe it's a lot to ask for audience participation over Zoom, but I'll try. If I were to ask anyone here, what's happening in this video? Does human intuition suffice?
Bouncing ball.
Okay, bouncing something, definitely. Yeah, probably not a ball because it doesn't seem to roll at the end, but something is bouncing, right? I think you know you have the right intuition, right? It hit something, right? There's a clear bounce, maybe right over here, and then maybe there's another bounce kind of over here, maybe, and then maybe a third bounce, maybe something else, some kind of wobble. All right, something's going on here. We have some idea what's happening, not a perfect idea. Okay, let's make that problem even simpler. Okay, if I gave you a trace in SE3, like looks exactly like this, then you'd be right. This is definitely a bouncing ball in this case. Okay. Now, I want to learn the equations of motion for this system, or identify the equations of motion for this system. And the problem right off the bat is that if I try to throw this at something like deep learning, even with lots of data, that deep learning is biased towards simplicity, right? If I want to learn f of x parameterized by theta, the biases from things like weight regularization lead you towards low Lipschitz constants, lead you towards smoothness in F. Right? What does F look like for this problem? This is my cartoon of F here for the bouncing ball. I'm mapping from current pose and current velocity to the next velocity. And it is not simple. You see the impact event here represented as this very stiff region of this function, right? Everything over here, I think, is not hitting the ground. Everything over here is hitting the ground. And so this function is not simple. At the same time, I would argue that this should not be a hard problem. All of our intuition can identify what's going on here, right? And there's a distinction, which is that while the dynamics are not simple, the geometry is. This ball is hitting basically a flat surface. And we might not be able to perfectly agree on whether it's flat or not, but it's flattish, right? And that surface is pretty simple, even though the induced dynamics are complicated. And I think this is a key insight here. All right. So before going into solutions.
Mike, if I interrupt you for a second.
Go ahead, yes, please.
Bill, if you'd like to ask a question. We can't hear you, Bill. Okay. Okay, probably we can come back to it later, but I still can't hear you. Okay, Mike, sorry about that. Let's continue.
No, yeah, anyone should feel free to interrupt with questions, and Bill, if you can get the audio working, jump right in. So we had this intuition that learning was going to be hard, and we wanted to sort of codify that a little bit more and share that insight, I think, with everyone else. And so we took a couple passes at this. So this first pass was from last year, purely looking at simulation, purely empirical, right? So we set up a learning problem where we took a cube and we threw it in simulation here in Majoko, and we varied the stiffness of the Majoko contact model. And we made this learning problem as basically as easy as we could make it, right? It's training on single-step predictions. It's being validated on single-step predictions. There's no distribution shift. We've optimized hyperparameters as best we can. And then we just looked at how well it did, and we're going to see how stiffness relates to the problem. So a couple of hypotheses here. One is that stiffness is inherently chaotic, right? If I were to go to Vegas and start throwing dice around, it'd be very hard to predict what happens to the die. This is just a hard problem fundamentally, particularly if it's stiff. And so this first loss here is saying, well, even if I use an oracle, right, the true model, given some measurement noise, how does that perform? And no surprise, but the stiffer it is, the harder it is the worse your oracle performance is, okay, even if the noise is the same. So that's not shocking, and kind of a known physical property. The next hypothesis here is to look at the training error, and here the training error as compared with the oracle, to try to take out this effect of underlying oracle error. And here what we see is that if the dynamics are stiff, it's actually really hard to get effective training. Our training losses are an order of magnitude higher than the soft systems, which is surprising. And I would be inclined to say this is user error had not some really smart students spent a really long time trying to improve on these results and consistently seeing large training errors, even with big, deep, over-parameterized neural networks here. So the underlying optimization landscape is what this is really saying, is poorly behaved. It is hard to train effectively with stiff dynamics, okay? And then lastly, we can look at testing error, again, as compared with training error. And we can see again that for the stiff dynamical system, you generalize poorly to unseen data. And in fact, even as you add more and more data, your generalization error hardly budges. So all this is really saying here is that if my underlying dynamics are very stiff, right, coming from a stiff contact system, then it's going to be hard to learn. And this is not a surprise, right? Stiff differential equations, stiff optimization landscape should be problematic, but I think it's something that the learning community is often willing to gloss over and just sort of hope that throwing more data at the problem will resolve the issue. Okay, so more recently, this is work that we're going to present in a few weeks months at L4DC this year. We try to back up this empirical result with something theoretical, and so here we're going to look at generalization error, which is how well does your learned function generalize to unseen data, and can you prove something about it? And so there's some nice results out there that basically say when evaluating unseen data, your loss can be bounded by something that looks like scales with the Lipschitz constant of your loss with respect to your parameterization and the amount of data you have. So the more data you have, the better you should generalize, but also the lower the Lipschitz constant is, the better you should generalize. Okay. And again, let's go back to our falling particle example, our falling ball example. And what we see is that because the dynamics you're trying to learn, even if all you're trying to do is learn the height of the ground, okay, even if all you're trying to do is learn a single scalar, so you've perfectly parameterized the problem, you made it as easy as possible, you see that the function you're trying to learn, dynamics, has this 1/dt coming from the discretization of the impact event, and therefore your loss function will have a Lipschitz constant of 1/dt as well. So if I'm trying to learn a stiff dynamical system, then inevitably I have this high Lipschitz loss landscape that can be hard to learn. And it's important to say this is true for really any parameterization of F. This is a perfect parameterization of F. I could use a deep network. I could use any kind of bag of functions, whatever you name it. This is sort of independent of the parameterization. That if the underlying dynamical system is stiff, then my loss function is stiff, right? And I'm going to generalize poorly. just a kind of a note, given the amount of attention that has been paid recently to differential physics. I think differential physics is very exciting, but there's a sort of an insight here, which is that, even if your physics are differentiable, right? Even if you use a differential simulator, if the thing you're trying to learn is stiff, it's still hard, right? This sort of, no amount of injecting differentiability or being clever with how you compute the derivative changes fundamental fact. Is your question?
Yeah, Arvind has a question, I think. Arvind?
Yeah, so the question about suppose 1 by dt parameterization, is that true even if you use, for example, an impulse formulation?
The discretization that I use specifically is an impulse. It's the Stewart-Trinkle discretization.
Okay.
Yeah.
All right. Okay. Okay. Thank you.
Yeah. The smaller the dt, the sort of the more closely you approximate the instantaneous event. Okay, so I think differential physics is a really fantastic tool, but let's be careful, right? How we deploy it. If we're going to try to just compute derivatives, and those derivatives are very, very large, then we may be in trouble when it comes to actually using these results. Of course, we can inject softness, right? So we can inject regularization or smoothing or soften the simulation, and that will make things easier, right? That's sort of another conclusion we could draw here. So where that's appropriate, go for it, right? And understand that's going to help out your learning problem. Of course, you're also changing the solution, right? So for example, if we're trying to learn this stiff function, we add a bunch of smoothing, we get this nice blue line here, for example. While smooth, it has changed the answer. Okay, so our sort of goal is to get the benefits of smoothing without changing the answer, without actually smoothing, and that's what we're going to show here. So one of the things we saw on this falling particle is that, well, even if you have the right parameterization, okay, even if you say I only need to learn where the ground is, the loss function is not good, and the loss function leads to stiffness. This loss function is your traditional loss function, which is you say I have a bunch of data and I'm going to make predictions on the next state, and I'm going to compare that to my data, and I'm going to square that, add it up, right? Our naive loss function. And we can see that here on this cartoon, where if I have a relatively stiff function in blue and I take some noisy samples from it, these little dots, and I want to make sort of look at my loss, well, the normal loss would say, okay, how well does this data point up here match the blue function? Well, I take X and I make a prediction and I compare the error and I get this sort of large pink line here. And it would say that this data point poorly matches my function because I have a lot of error. When in reality, maybe my noise was really just in the X direction. And so you might say something like graph distance or total least squares would be a better loss function. So graph distance here shown in purple. And that makes a lot of sense. Of course, graph distance, is very hard to calculate, right? Computing this optimization problem over the delta X component is potentially intractable. So we're going to do something inspired by graph distance. To be inspired by graph distance, first, let's think about this implicit physics formulation where we say, well, for the case of my falling ball, my next velocity is my current velocity minus gravity plus some contact force. Okay, and that contact force is constrained by complementarity. This is our same complementarity formulation. Okay. And I'm going to write a new loss function which says, don't make predictions, don't compute f of x, compute this f bar of x, is this implicit formulation, where now I have to guess lambda. So I'm optimizing over lambda on this inner loop. And I want to say I should also have this a low complementarity violation here. So however I want to define violation of this constraint, I want that to be small. Okay, so if the complementarity violation is 0, then I'm back to my original physics formulation when I'm doing simulation. But if complementarity violation is non-zero, this formulation allows you to balance physics violations with this prediction term. Okay. Well, I'll show some cartoon here in a second, but the key insight here is that this preserves the original solution. So the true solution is still the original solution for theta was still the right solution here, but it dramatically reshapes the loss landscape. Right? So this is for our cartoon problem here. This is loss versus theta. With this implicit formulation here, we have the solution in the solid purple, the naive prediction version with this very, very stiff dashed line here. Right? And obviously, we'd rather be optimizing over the dark purple version here, this implicit formulation. And notice again, it doesn't touch the global optima, right? So we've added this kind of epsilon smoothing, but we've not added epsilon smoothing to the physics. We've added epsilon smoothing to the optimization problem for how to train this. That's, I think, the sort of the gold standard here, right? We've made an optimization problem easier to solve without introducing a fudge factor.
So can you give some examples of this complementarity violations? Like what would be the physical intuition for it? Does it mean, is it similar to allowing some penetration, or like?
Okay, so that's a great question. It is similar in spirit to allowing penetration. So for example, we might, in this case, I think the complementary violation is really just the force times the distance, so the product here. I would say it's only similar in spirit to allowing penetration because we're not actually simulating here. That, I think, is the key difference, is we're taking advantage during training, only during training, of knowing of the fact that we know the state transition. I know X prime because I've measured it from data. So I'm not making predictions about X prime. I'm really just trying to ask the question, how well does my model match this observed state transition, X to X prime? And so from that perspective, I can say, well, pretend you're simulating, right, but allowing some penetration. But you're only allowing penetration if it helps you make a better prediction, if it reduces this first part of the loss. Okay.
And
now,
if I may ask another related question. So I know that this is like some sort of a softening of this constraint, right? Like, have you tried looking into an approach where you actually solve that optimization problem with respect to, say, allowing these, such that it always satisfies the complementarity constraints?
Right. So if you basically take this complementary violation and move it down into a constraint, okay, that's really the same as just calculating f of x. That's simulation, and your loss function now is this dash line, this pink and dash line. So you can do that sometimes, but the landscape is very, very hard to work with.
I see. Okay. Cool. Well, that's great, actually. Yeah.
I'll try to give a little more sort of higher level intuition here as to what we're doing in a second here. So this is really just a form of implicit learning.
So
it's very
Matt
closely
also has a
related.
question, if I may, sorry, interrupt you again. Matt,
go
please
ahead.
go ahead.
Can I say that again?
Matt also has a question. Matt, please go ahead and ask a question.
Sorry to interrupt you. So you've traded something where the loss is linear in the Lipschitz constant to something where it's quadratic in essentially in your smoothing constant. Is the smoothing constant much larger, or why is this an improvement?
Epsilon we can pick. So we picked this to be something like 0.1 or 1.
So it's large, quite large.
Compared to 0, yes.
Yeah.
I don't know. Yeah, I don't know what's it's a weighting parameter, right, in terms of these two different optimization objectives. So we do want both of them to matter in the inner optimization problem.
And what if you went back to the original problem and you didn't sample with a regular delta t, but I mean, it's essentially like a total least squares where delta t or delta x can vary, no constant sampling rate.
Say that again.
What if you? So your initial formulation, it has this Lipschitz constant because you're presuming a constant sampling rate.
The Lipschitz constant really comes from the physics, right? And then when you discretize the physics, you get a 1/dt. So
right.
So
but if dt varies, and you're just free to drop small dt's.
The dt is I mean, you can downsample, right, and get a larger. Maybe this is what you're asking. You can downsample and get a larger dt.
Right. These are all ways of coarsening the problem.
Right, you're coarsening the problem, and you're learning a worse model at the end of the day, right?
But isn't that also true with the implicit formulation?
It's not. So one thing I can say, for instance, if you look at the noiseless case, right? If there's no noise in the data, and you have the right model here, so theta is correct, then you're going to achieve zero loss. You're going to achieve zero complementarity violation, and you're going to achieve zero prediction error. So in the noiseless case, we haven't changed the global optima, and that I think is a key part of this formulation here. Noise will never really add a little bit of bias, and we haven't gone and characterized that theoretically. At least in the noiseless case, we actually don't change the problem at all at the solution. We just change the problem around the solution to make it easier to optimize.
Sure. That would also be true in the total least squares formulation.
Well, no, I think, okay, so totally square, I mean, I have no problem with totally squares. I just think totally squares you can't calculate. Right? The optimization problem for totally squares is harder because now you have your delta x is inside your f up here. And so if f is complicated, now this is a nonlinear optimization problem. Whereas I didn't give the details here, but this optimization problem we posed is actually a QP.
Oh, okay. All right. So continue. I mean, I get what's
Good
going on.
questions, though. I'm happy to do as much discussing as you want. Okay, just to give some sort of higher level insight here. This is a form of implicit optimization at the end of the day. It's closely related to energy-based learning. So your general explicit learning would look something like this. I learn f of x, such that x maps to y. Implicit layer might look something like this, where you get to learn f of x comma y, such that it's equal to 0, right? So the output kind of feeds back into the input. Very popular lately have been learning formulations that look something like this with an optimization layer. This is just a different form of implicit optimization, where we say there's a slack variable now, or y is really just the argument of some optimization problem. Okay, that's x, y. Our formulation is a variation on this. It actually looks a lot like this, where we say, okay, I'm going to learn some function g of x lambda, excuse me, where lambda is the solution to an optimization problem. So it's kind of a specific blending of this optimization layer. And the normal approach here, this is basically simulation, right, would be to say, okay, learn this implicit optimization implicit structure, and then do simulation to compute a loss. Okay, this should be sort of the standard thing. What we're doing actually just looks like this, which says, for training, again, for simulation, solve the real problem. For prediction, solve the real problem. For training, take advantage of the fact that you know why, right? You've observed why. And now we form this single optimization problem, this implicit loss function, where we optimize over lambda, balancing out the H objective with the G, the prediction matching. Okay. And I think, this is something where we're still kind of scratching the surface, but I think this is a structure that, really could be widely applied to problems where you're expecting, these meaningful slack variables, these lambdas to exist. You're expecting stiffness in your underlying problem. And you have this additional property that this H function, is going to be 0. In this case, our complementary loss. We did talk about totally squares. For robotics problems, we can actually relate this implicit loss to graph distance. We can go through the math and compute the relationship. It's not always possible, but we can sort of bound that relationship sometimes, and empirically, it's been quite effective.
So if I may ask this question, so does it matter, I mean, so if you probably stay in the same mode, right, then probably there will be, you already don't have that problem of complementarity. So do you have problems tuning this hyperparameter epsilon when, depending on what kind of data that you have, because you might actually change mode only very few times, right? And impose those constraints. I mean, you need to make sure that those constraints are sort of satisfied during those times, right? But you might have very scarce data, when you're doing the mode switching. Does that actually create a problem, or you haven't seen that while training?
I think there's a few ways to answer that. So you're definitely right. If you're not seeing mode switches, then you don't need any of this, and it's not going to help you any, right? This is all for the goal essentially of simultaneously identifying the mode boundaries and the dynamics in the modes at the same time. And I'll show an example of that in a second, an explicit example of that in a second. If you have sparse data, yeah, I mean, that's always going to be problematic, right? If you're trying to identify modes and dynamics simultaneously, you're going to need sufficient data to do so. I will say we've done, we've been pretty effective. Maybe I'll preview a result. So for that cube tossing problem I showed before, depending on how much structure we impose on what we're trying to learn, with about 5 or 10 rows of the cube, we can identify things about as accurately as you're going to get. You need to see enough contact on all the different surfaces, right, to identify them. If a corner doesn't hit the ground, then you're not going to identify it, that it exists. But beyond that, we do see pretty good data efficiency. But something we're still exploring for sure. Okay, back to that comment about identifying the modes and the mode boundaries explicitly. So here's a related paper, also L4DC this year, where we're trying to identify linear complementary systems. This is really just a piecewise-affine learning problem, where we have potentially thousands of pieces that are coming from a high-dimensional problem. Also to this question earlier of choosing epsilon. For this paper, we actually went through different choices of epsilon and tried to understand how that affected the solution. And there was quite a broad range of choice of selections there that had minimal effect. It had to be big enough and it couldn't be too big, but within a few orders of magnitude, it didn't seem to matter that much. So here I'm showing an animation of learning a toy problem where we're identifying the mode, which is the color of the dot, and the prediction, which is where the dot is. These are just iterations through the optimization procedure here with a fixed data set size. And you can see it, taking gradient steps. This is just running Atom, taking gradient steps to move the mode boundaries and fix it, learn the dynamics simultaneously. And this exciting thing here is this scales to dimensions of lambda in the tens, which is leading to really thousands of potential modes being identified without any kind of clustering, without any kind of a priori mode identification. Okay, so now looking at some real data here. So this is the cube tossing problem. So we have a data set. The first data set was with hand tosses. Now we're collecting more data with the robot doing the throwing of tossing this cube using April tags for motion capture, and the process of removing the motion capture part here. And if you take our data set, which is a few hundred rows here, and you give it to an unstructured network to do prediction, you get the result here on the right, which is good, but not great. It really gets the orientation quite wrong. It doesn't understand that it should come to rest on a face and so on. It gets kind of the bulk motion more or less correct though, but really misses orientation. This is just, our kind of original intuition here to reinforce what we've been talking about. If you look at how your simulator works, right? All the hard part is really in this contact force solver block, right? You have your continuous forces, you have your collision detection and your geometry. That may be slow, but it's not computationally stiff. And this is sort of where all the stiffness is. The non-smoothness is stuck in the contact force solver, which is that basically solves the complementarity problem. Okay. So what we did in this work called ContactNets is we said, well, rather than try to learn this end to end, right, x u to x prime, we're just going to learn kind of these two bits up here, the continuous forces and the contact geometry and the friction. The first paper, actually, we didn't learn the gravity, but since then we filled that in. So we're going to learn basically geometry and continuous forces, and those together implicitly define the net force. And because these geometry is nicely behaved, even though the state transition is not, this should be better behaved, better aligned with our deep learning biases.
So Michael, we have another question from Kong. Kong, if you can go ahead and ask a question.
Hello. So Michael, I actually had a quick question from the previous slide about capturing the motion of dropping. So I'm assuming that the throwing motion of the robot arm is very consistent. And my question is, when does the noise comes in is it usually on the first, like you probably will land on one corner and the motion is gonna start being unpredictable?
For data collection, we randomize the toss. So
Okay.
the robot could be consistent, but we're not letting it be.
Then if that's the case, would the landing be repeatable, like the trajectory? Like, would you get the same trajectory if you, like, basically I'm asking if the model is repeatable.
I'll show you a video at the end that will give you an idea of what I think is good prediction. But the answer is, will it be perfect? No. We're talking about basically, going to Vegas and predicting the outcome of a die toss. This is a chaotic system at the end of the day. And so it doesn't always get the face it lands on correctly, but it often does in this case. I mean, it's not like it's not really a craps table, right? It's not rolling that many times. So it should be sort of possible. Does that answer your question?
Yes, yeah. At the end, yeah, I can ask you more about your end. Yeah.
Okay. So the intuition here is kind of the same intuition. I'm a little backwards chronologically here, but the idea again is to say, for computing my loss, I don't want to simulate. Okay. And this is why I sort of rebel a little against this idea of differential physics here as the key tool, because simulating is going to be inherently stiff. It's going to pick up all the stiffness of the underlying problem. Instead, we're solving this implicit loss. In our case, it's the case of contact specifically here. It's a QCQP. So we're embedding the true friction cone here as a constraint over candidate forces. And those loss terms look kind of like what we saw before. The first loss basically says that we want to match the observed motion. And the second loss has terms, and maybe this answers your question a little bit, Devesh, from earlier, that look like a complementarity violation, a term for maximal dissipation, and a term for non-penetration. Okay, all over candidate forces for lambda. Okay. And then the net result we get, and here's a video of 4 different tosses here. You can see that's qualitatively pretty good. It doesn't always get the number of tumbles correct, or the net face correct. But if you look at the trajectory error, so here's integrated error over trajectory. If we introduce a pretty strong prior, which is to say the thing we're trying to learn is a polytope, and we don't know exactly what type, we know what shape it is, but it's a polytope and it's interacting with the flat ground. Our training curves are here shown in blue, which is to say, 5 to 10 tosses, somewhere in this range, we're doing quite well in terms of predicting geometry and predicting performance. All right, we're looking at something like 20% of the block width as integrated error, average error, and maybe 20, 30 degrees of rotational error. If we don't throw any structure at the problem, the deep network is basically random when it comes to orientation. Right? You're looking at 40, 45, 50 degrees of error, even at the high data regimes. Okay. The purple line here is an interesting one. This was our first attempt at using a deep representation of geometry. So here we're using a deep network to represent a signed distance field for the object. And it worked okay with a lot of work, a lot of effort, I would say, went into the purple line here. And I'll come back to that in a second. But it showed that basically we can be data efficient. Obviously, you need more data to learn a deep network, but still good long-term prediction performance. That said, like I said, it was hard to learn geometry as a signed distance field. And since then, this is unpublished, but we've been looking at representing objects via support functions. So here we're learning a support function, which is a common representation in computer graphics to define a convex object. So we're learning a deep network here that's homogeneous and input convex. And this works just fantastically well. We can learn complex geometries from relatively small amounts of data. The code at this point, Matt's done a lot of work on the software, which you can check out on our website. It's gotten quite adept at this. I think we're planning to run a live demo at ICRA. So if you want to come by the booth or come by, if you're anyone signed up for the GRASS demo, we're hoping to do this live to basically collect data and learn geometry in a couple of minutes, all starting from scratch in a live online fashion. So that's the hope for ICRA. And then just to wrap up, because I want to leave more time for discussion, we have some good questions here. I think this is just a start, right? I said at the beginning that we really wanted to talk about physics-inspired fundamentals, and that is the case. I think we need as a field to get to the point where we are data efficient, where we are able to act in these unknown environments. And I think we have a long way to go to getting to anything near human-like. But I would argue pretty strenuously, right, that there's no such thing as standard learning or generic hybrid approaches, that all those ideas have some kind of structure or bias embedded in them. Standard learning, for instance, would say, that I have weight regularization or some kind of weight decay. And that inherently clashes with multi-contact robotics. So we should be thinking about ways to encode structure or bias that are more appropriate for our problems. Ongoing work is to get rid of the able tags, as I said, and replace that with computer vision. I'm hoping to show that at ICRA, but we'll see. And also looking at the role of tactile sensing as well in this domain. I didn't talk about our CASI work at all, but that's another sort of whole thrust in the lab, looking at running and jumping on CASI and different control strategies for how to handle impacts, for instance, when landing. And then lastly, there's a gap still between what we can learn, which is a complex dynamical model, and what we can control with, which is a relatively simple model still, right? We can do multi-contact control, but not with 20 degrees of freedom and 10 contacts. And I think in between there is, what do we want to learn, right? We don't need a model of the entire world or every object we might encounter. And so we need some kind of task-driven edge here that's going to say, I'm going to learn a simple model that's appropriate for a task so that I can then use it in an online fashion. This is something that we're actively working on as well. With that, I want to thank all the students who did the hard work here, and thank sponsors as well, particularly for this work. A lot of it came from NSF, Google, and from TRI. I'd be happy to take any questions.
All right, thank you very much, Michael. And we already have a question from Daniel. So Daniel, go ahead.
Yeah, so Michael, that was a great talk, and here you're solving extremely complicated learning problems, right? So you're trying to learn chaotic dynamics, and the way you're doing it is by learning essentially deterministic chaotic models. So coming back to the question actually that Kong asked about uncertainty. So what happens if we replace deterministic chaos with just a quantification of uncertainty, and then use it in a stochastic MPC setting, kind of giving up on the idea of predicting the trajectory exactly, recognizing that there might be a bifurcation going into different modes, and then quantifying many possible things that can happen, right? And then sampling this model, doing, say, scenario-based optimization, wouldn't that be a more reliable approach to deal with this incredible complexity of the chaotic model?
I can't disagree with you. I think it's a good comment. I would say I'm very interested in trying to understand what a good stochastic model for this type of system would be. I don't think anyone really has a good answer to that. I've seen various takes on like stochastic complementarity systems, but those are often derived from the perspective of mathematical convenience as opposed to any kind of real connection to underlying uncertainty in the real system. Which I don't want to say is wrong, but it's not clear that it represents actual uncertainty. So I want to first understand that uncertainty. And that's sort of one of my side hopes from the data collection we're doing with all these different tossing experiments, is that we actually can go on and try to characterize it somehow. I guess the other comment I would say is stochastic, control in a stochastic system is even harder than control in a deterministic system. So I'm a little scared of where that might lead and how we would actually solve that fast enough. But I think your intuition is definitely correct. That these systems are chaotic and they are hard to control. And for many scenarios, we probably do really care about some kind of multi-hypothesis planning where we take an action and we might end up in a few different modes, and we want to understand the implications of both possibilities. I think that's totally correct.
Right. So yeah, I very much agree with you that many people are treating uncertainty just as a mathematical and computational convenience, right? Although the planning problems are they're relatively simple algorithms like Pegasus that you just draw from exactly the same sequence of random numbers and then you average over a number of scenarios. That's fairly simple, I would say. Given, of course, that the stochastic model makes sense physically.
It's the computational side, I guess. I mean, we're sort of struggling to get real-time performance with the deterministic model right now, and I would, yeah.
Of course.
We have another question from Scott. Scott, go ahead, please.
Thank you. Very nice presentation. I appreciate the time you spent talking about very stiff bodies colliding and the challenges. So my question is this very fundamental question. So the very basic model here is, a complementary condition together with a set of differential equations. Now, suppose I have a set of rigid bodies, some in contact, some in not. Is that model a complete description of the physics?
It is a complete description of the physics. I think even complementarity itself, right, is not perfect. There's some nice examples. There's a paper by Chatterjee back a long time ago looking at how, in fact, complementarity is actually not the limiting behavior of stiffness for some like a rod falling. So it's certainly an approximation of reality, or when reality here is like stiff, very, very stiff mechanical systems, right? The material stiffness at play. But in the sense that it's a good approximation of one body, it's, I would say, also a good approximation of multiple bodies. The one thing you can run into, maybe you've seen this before, is you can actually run into like non-uniqueness as an outcome here, particularly with friction involved. And so that's something that we've looked at. Actually, we did some work on like simulating and sampling from non-unique possible outcomes to simultaneous impact events. I think that was sort of really fun mathematically. At the moment, we're definitely skewing towards imposing uniqueness is not really that much to assume. And if we can't assume uniqueness, then our planning is in trouble anyway. I don't know. We've kind of hedged our bets on both sides of that question, I guess.
Yeah. So I suspect that it's not, and it's missing the physics of collision. It ignores that and assumes what you know before the collision and after the collision. And of course, there's a change of state, which is impulsive or whatever between those. And that's not a complete, you're missing some physics, and therefore,
I'm not sure what you mean.
If you have a set of bodies put together, the behavior after a collision and before a collision depends on the material properties and how shock waves propagate through those. It depends on the geometry, and of course that's not at all part of the model. So I suspect this is why fundamentally these approaches have difficulty with very stiff systems. I also don't think they conserve energy. And that's pretty easy to show.
I'd be happy to talk about sort of the dynamics termination, maybe offline, but there certainly are problems with these discretizations. So this is what we've been using right now is an inelastic impact variation. Yeah. So everything is assumed to be inelastic. There are versions which assume elasticity. They're a little bit harder to get to work. They often require like subsampling your time steps. These models do have impact events. If you include elasticity, you can include things like configuration dependent elasticity, although most robotic simulators don't, because we don't have a good idea of what that elasticity should be. But it's not it could be incorporated into the modeling framework itself. As far as energy conservation, it really depends on exactly how you encode the complementarity problem. Some versions are guaranteed to conserve energy, and some can create it in different scenarios. I think that you can get versions which will conserve energy for sure. But the last thing I guess you said is sort of why things don't work for learning these systems. I mean, the vanilla algorithm we're comparing this to is learning a deep network that just makes state transitions. So it doesn't have any of the structure built into it. It's just trying to predict from current state to next state.
Yeah. Okay, thank you. I don't want to consume all of the available time here, so I'll be quiet.
There's another question from Yuki. Yuki, go ahead, ask your question.
Yeah, thanks so much for your great presentation. So I have a question on, I think your ADMM part, I think your model-based controller part. So I think you said that, you know, your control's frequency for this specific example is around 30 Hertz. I think this one, yeah, 30 Hertz and with 36 hybrid modes, something like that. I don't remember exact details. Yeah, I think this one. Yes, I think this one. So I'm just wondering, so fast. So I think here you assume you consider linear dynamics, all right? I mean, with complementarity,
Yeah, it's a linear complementary system. So we've linearized basically geometry and linearized the smooth parts of the dynamics, but not linearized the contact.
Yeah, I think my question is very simple. So would you think, I mean, would you face any case scenario where you may need to consider non-linearity in the dynamics? I mean, in addition to hybrid dynamics, in other words, would you think if you need to consider non-linear hybrid dynamic system in the future, if you want to consider more complicated problems such as, I don't know, acrobat with word, or I don't know, Lego robot, or manipulation? Yeah.
No, that's a good question. Definitely, right? I mean, I think even you see kind of the limits of linearity for these, you know, sweeping through this 20-30 degree rotation here.
I see.
I think there's a couple answers there. One is, you know, we're looking at things that basically take a plan as a nominal and linearize about that plan. So then you can get a time varying. I keep using the word linearization, but it's just linear complementarity linearization. I think that's one approach. I think you could also just start with the nonlinear system and try to solve it. That, you know, obviously the challenge you're going to run into there is the computational side of that. But I think we will definitely see cases where that's going to be important. And I don't know how we're going to scale to that. One approach we've been trying lately is to learn linear complementarity representations, even of the underlying nonlinear system. So from data, learn the linear complementarity version and then try to use that for control. And if the hope maybe is that if we do this in like an on-policy fashion, where we're looking really at solving a set of tasks, that the linear complementarity will be good enough to describe a set of tasks, even if it doesn't describe all the nonlinearity outside of that task relevant domain. But that remains to be seen.
I see. Thanks so much. And another question is, I think for your ADMM-based controller, in the second stage, I guess you solved this complementary, yes, exactly this part, I think in your second stage projection onto complementarity. So even for this system, linear dynamics with complementarity system, once you have so many, you know, hybrid modes, even with linear dynamics, I can imagine, I don't know, I think you use MIQP to solve the second stage, or you may just solve nonlinear programming with complementarity constraints. I don't know exactly how you solve it, but do you have any, you know?
Yeah, that's right. I mean, this is not going to scale to like, as the dimension of lambda gets bigger and bigger, right? You're always going to run into this fundamental scaling challenge here. So this is not a panacea by any means. I think it gets to more modes than we've seen before, but it's not going to scale indefinitely. I think, so right now we're solving this, depends on the example, but often via actually solving the MIQP for the projection. I think we're going to need the next question really is, what are the right heuristics here for this projection? As I said at the beginning of the section, I've totally given up on optimality here. I think optimality is never going to happen for this kind of problem, due to the NP hardness of it. So really, it's all about finding effective suboptimal solutions. And I think the consensus formulation, and I think ADMM is one nice approach. And I think looking at this heuristic is how we're going to squeeze out more speed from this.
I see. Thanks so much.
Although I said right now, for like a full robot, like a robot hand kind of problem, this QP is actually becoming more and more important. So we're spending a lot of time in stage 1 as well as we try to scale up.
Thanks so much.
We are having a lot of questions. So Kong, go ahead and ask your question again. Great.
I'm actually I was happy with the video that was showing about dropping the block. So I actually wanted to learn about the tool that you introduced towards the end about shaping the convex geometry, and how did that help in the research of the block, the dropping the cube.
That's in particular.
Yes.
So this is a representation of geometry. So if I want to say, like, I want to learn arbitrary geometries, right? We had first said I'm going to represent geometry via a sign distance function. And it turns out it's really hard to define what that means. Sign distance functions have particular structure, and it's hard to encode that structure on a deep network. And without any structure, your deep network kind of falls apart. In this case, in our cases. So here we're learning a deep network with some structure. It's input convex and it's homogeneous. And that network is the support function. The support function essentially defines distance to the surface of an object given a unit vector. And so the video here I'm showing is really actually training epochs here, where we're learning this deep network, we're visualizing the resulting geometry. During the training process, we do collision detection and so on with this geometry. We're using a lot of Drake here for simulation and for collision detection as a software library. I don't know if I answered your question though.
Yeah, I was trying to, because I think towards the end it was a little fast, and thanks for getting back to it.
Okay. Does anyone have more questions? Abraham, go ahead. Yeah, Abraham has a question.
Hey, Michael, thank you for the talk. I was actually going to ask a follow-up question on this. Were you using the support functions itself to impose the structure on the previous slide where you had the ContactNets and you assumed a structure of polytopes? So was that the same way by which you impose the structure?
This is our really probably our attempt to replace the purple line with something that works as well as the blue but has more generality. Yeah, so no longer assuming polytope, but also getting more data efficient training without a lot of hacking.
Oh, I see. So the support functions was the ContactNets deep.
Yeah, it's the figures here are from the paper, so this really is the time distance function. The support function is something we haven't published yet.
Okay. So then, can you tell me a bit more on how you impose a polytope as additional information on your contact description?
In this case, the thing we're learning is not a deep network. It's actually just the vertices of the polytope in the local frame.
Oh, I see. Okay. Got it. Thanks.
Okay, thank you. And Diego has a question. Diego, go ahead.
Yeah, hi Michael, thanks again for the talk. My question was a slightly different topic, because in the beginning you started talking about system identification now, and I think you're referring to the parameters of the neural network that you learned. I was wondering, like, for example, in the MPC formulation, or where you have the linear complementary system before, right? And then you have all these matrices A, B, and then E and F in the complementarity. Have you tried to, how do you get that parameters? Have you tried to do system identification through a complementarity system? Does it work?
Yeah, that's I know I went through very quickly. That's this paper we have at L4DC this year. We're actually learning those matrices for our linear complementarity system. So this is all synthetic data at the moment here.
Okay.
We're doing that for like 10 plus complementarity variables.
Okay, nice. So you had no problem on the fact that there was the actual complementarity constraints that you have to regress through, because
That's where the implicit structure, I think, really helps. Yeah.
I see. Okay, great.
We have numerical comparisons there of say, directly simulating through the complementary constraint, differentiating through the complementarity constraint versus the implicit formulation in terms of how they performed on the synthetic data.
Nice. I will look in the paper then. Thanks.
If I may ask a few questions. So similar to the MPC, when you said, right, like MPC has, of course, the compute disadvantages if you have more complementarity constraints. Do you see like the learning problem where you're softening the complementarity constraint? Now, if you have, instead of one complementarity, if you have maybe multiple complementarity constraints, does that affect your learning rate, or does that affect a good learning model that eventually you get out of it?
I mean, we definitely have multiple complementary constraints in all these examples. So other than the falling particle example, which is only one, everything else, the cube, what I'm showing here, all has lots of complementarity constraints involved for friction, for normal force, and so on. And yeah, I mean, that's the hard part of the problem at the end of the day, right? That's where all the intellectual effort has gone on our end, is to try to handle those constraints in a way where we can differentiate across them effectively. Right? We could do sort of the differential optimization thing and solve them and differentiate them, but that doesn't give you any information about crossing the mode boundary. And so a lot of this work is on sort of how to get that information back into the learning framework. And yeah, I mean, the more they are, the harder the problem is. I think we found that this style of approach can scale really well, surprisingly well, to large numbers of constraints.
That's really good.
Not perfect. I mean, I'm showing success here. These, at the thousands of modes regime, it succeeds about as often as it fails, which is not bad. You can always, random restart and try it a few times and eventually it works, which I think is sort of the state of the art in learning anyway. But it's not like the optimization landscape is not convex, right? So it doesn't, we don't always hit the global minimum, but for sure, we hit it reliably enough where I'm happy with the result.
And the initial work that you were showing, like for doing the contact-aware controller, have you guys also looked into? I assume that work is assuming a linear complementarity system. Have you sort of looked into problems where you have a non-linear system and then you're trying to do some local control with that?
Yeah, we're trying this right now for manipulation problem. So we have with the three-fingered hand. We're trying to connect these ideas. In fact, learn the model. And then do control on it with MPC. That's very, very ongoing. So nothing I can share just yet. But
I see. But the learning results, like sometimes, I mean, even though the learning results look good on paper, but once you go towards controlling them, they seem to be very off, right? Because the errors propagate and then they accumulate very fast. So,
yeah, I guess we have learned the dynamics of the cart pole with the walls and applied the control to that, and that worked. It's there's a little bit of grain of salt in there that the data, to collect data, you have to have a working controller. So it seems a little kind of pointless to have a working controller, learn a model, and then get a working controller out of it. But we have at least demonstrated that on this system.
I mean, the problem being that you need to get to that sort of, you have to stabilize the system there to collect the data and then sort of learn the model.
Yeah, right? Yeah. So we're trying on the robot hand right now. That's ongoing. I think early results are optimistic, but very preliminary.
That's cool. Yeah, so those were most of the questions I had. I was also interested in the MPC problem that you showed, but I think Yuki asked most of the questions that I had, so I think that's covered. I know if other people have questions, please go ahead and ask. It seems that's pretty much, so thanks again, Michael, for this great presentation. I think it was really interesting. I think people had a lot of questions.